In this video, we're going to talk a little bit about the process of factoring a polynomial over the integers or over the rationals. So here I've put three polynomials. One of them is x squared minus 5x minus 14, then there's 3x squared plus 9x plus 15, and then 2x squared minus 7x plus 2. What happens when we try to factor each of these polynomials? We'll just go through one by one. The first polynomial, x squared minus 5x minus 14, if we want to factor that over the integers, we just remember what we did in high school, which is we think about two factors of negative 14, which would add to negative 5. And I know that those would be negative 7 and 2. So based on that, I know that this will factor into x minus 7 times x plus 2. That's a valid factorization. Therefore, this polynomial is not irreducible over q. It is reducible. Okay, the second one, 3x squared plus 9x plus 15. One thing you probably learned to do in school is first scan to see whether there are any common factors among all of the terms, any common numerical factors that you could factor out. And in this case, there's a 3 in each of the terms. So if I factor that out, I will get 3 times x squared plus 3x plus 5. So in this case, it looks like this polynomial, x squared plus 3x plus 5, I would need to look for two factors of 5, which add to 3. And I just don't think they're there for the taking, not in the rationals anyway. I can factor 5 into 5 and 1, and those would add to 6, or negative 5 and negative 1, but neither one of those will add to 3. So I think this polynomial is irreducible over q, though it's not irreducible over the integers, because there's this factor of 3 that can be pulled out. And that 3, it is a unit in q, but it's not a unit in z. All right, and finally we have 2x squared minus 7x plus 2. For this one, if I'm factoring over the integers, I'm probably going to try and factor this into something involving a 2x times something involving an x. I know that there's no common numerical factor that I can take out because here I have 2's. The only factors of those are 1 and 2. And here I don't have a 2. And there's no sense in pulling out a 1. So I try splitting into 2x plus or minus something times x plus or minus something. And I might even go so far as to say, because the last term is positive and the middle term is negative, I'm probably going to need two negatives if this factors at all. But then at that point, I think I'm stuck because I can put a 1 here and a 2 here, or I can put a 2 here and a 1 here, and neither one of those options gives me a minus 7x for the middle term. So I think at this point I'm stuck. Cannot factor this way. So this is irreducible at least over z. And the theorem that we are working up towards here is proving that if this polynomial is irreducible over z, if there's no way to factor into polynomials over the integers, there's also going to be no way to factor over the rationals. But we will prove that later. So taken as a whole, these three examples are meant to serve as motivation for a certain idea. In this first example, we had a polynomial that was not irreducible over q, it was reducible, and was also reducible for that matter over the integers. In this example over here, we had irreducibility over the integers, and by a theorem that we are going to prove later, we therefore have irreducibility over q. But in this case, we have something in the middle. We have a polynomial that is reducible over the integers because there's this common factor that can be taken out, but still irreducible over q. And the reason that this conflict occurred, the entire reason for it was we had this common numerical factor of 3 that could be taken out of all of the terms. We had a constant that could be factored out, and it was a non-unit in the integers. So this is a definition. This is called the content of a polynomial. If f of x is equal to am x to the m plus am minus 1 x to the m minus 1, etc., down to a1x plus a0, and this is a polynomial in z bracket x, a polynomial with integer coefficients, then we define the content of this polynomial as follows. The content of f of x is the GCD of am minus 1, etc., all the way down to a0. Okay, so the content is the GCD of all of the integer coefficients. And one more definition while we're at it. We say f of x is primitive if its content is 1. So for example, this polynomial is primitive because the GCD of 1, -5, and -14 is 1. And this polynomial is primitive because the GCD of 2, 2, and -7 is 1. Because we're looking for the greatest common divisor of all of the coefficients, and there is no greater divisor that divides everything there. But here the content is 3, because 3 divides each of these, and there is no greater integer which divides all 3 of those. Therefore, this polynomial is not primitive. Now, one thing I wish to be very careful to point out is that primitive sounds like it derives from the word prime, and in a way it kind of does, but primitive doesn't mean prime or irreducible as a polynomial. And a good example is over here. This is a primitive polynomial. It's primitive in z bracket x, it's primitive in q bracket x, and it is irreducible in neither of those. It is absolutely factorable. So primitive doesn't mean prime or irreducible. We should just think of it as an indicator that the terms of the polynomial don't have any numerical factors in common in the integers. Now a little bit more about this middle example here, 3x squared plus 9x plus 15. One thing you'll notice is the content of this polynomial was 3. 3 is the GCD of the coefficients. But when we factor out that 3, what we are left with appears to be a primitive polynomial. And that is a lemma that we're going to prove now, that even if we start with a polynomial that's not primitive, we can get down to one that is. So here's a lemma. If f of x is equal to am x to the m plus etc. a1x plus a0, that's a polynomial in z bracket x. And let's assume that am is non-zero. And the content of f is d. We'll call it d because it's the GCD of several numbers. Then f of x can be expressed in the form f of x equals d times g of x, where g of x is primitive. And you'll notice here I'm not assuming that f of x is not primitive. I'm just thinking, we don't need a separate case for this. If f of x is primitive, then its content is 1. So f of x is equal to 1 times the same polynomial, which was primitive to start out with. So what we're going to prove is that in any case, if the content is d, then we can factor that out and leave ourselves with the content times a primitive polynomial. So let's prove that. All right, so let's assume f of x is equal to am x to the m, etc., down to a1x plus a0. And as always, we assume that's an element of z bracket x. And let d be the content of f of x. So d is equal to GCD of am minus 1, all the way down to a1 and a0. It's the GCD of all those numbers. So let d be the content of f of x. Then, since d is the GCD, it must divide each of the coefficients. So d divides am minus 1, etc. We can write aj is equal to d times aj prime for some aj prime in the integers for every j from 0 all the way up to m. Okay, so in other words, we're going to go and do the work of factoring out d before we get started with factoring the polynomials. All right, so each aj is expressible as d times something. So then f of x is equal to am x to the m plus am minus 1 x to the m minus 1, etc., down to a1x plus a0. And the next line, that is also equal to dam prime x to the m plus dA m minus 1 prime x to the m minus 1, etc. down to dA1 prime x plus dA0 prime. And then we're going to go ahead and pull out that d, factor it out, leaving ourselves with another polynomial inside the parentheses. All right. And then that thing in the parentheses, that polynomial, is what we're going to define to be g of x. And it may seem like we're done. Now we have our d, we have our g of x. But before we're done, we need to show that this g of x really is primitive. So why is g of x primitive? Well, to show it's primitive, we need to know that its content is 1. We need to prove that the GCD of all of these coefficients, am prime minus 1, or sorry, am minus 1 prime, a1 prime, a0 prime, that the GCD of all of those is 1. All right, we know that 1 divides all of them. We just need to show that nothing greater does. So if the content of g of x were equal to, let's call it c greater than 1, then we'd have c divides am prime, c divides am minus 1 prime, etc., all the way down to c dividing a1 prime and c dividing a0 prime. But then that would mean that each of those coefficients, each of the prime coefficients, can be written as c times something. So am prime would equal c times am double prime. And I promise there's not going to be more than double prime in this video. But a1 prime will equal c times a1 double prime. And then a0 prime equals c times a0 double prime for some a0 prime, etc., double prime, am double prime in the integers. And you can probably see where the problem is going to come from here. I'm just going to zoom out so we can keep the entire proof in frame here. There we go. But then what does this mean about the original coefficients? Well then, that means that am was equal to d times am prime, which was equal to c times am double prime. And then am minus 1, that was equal to d times c times am minus 1 double prime, etc. Each of the original coefficients is divisible by d times c. So dc, which is greater than d because c was greater than 1, and dc is a divisor, common divisor, of a naught through am. That's a contradiction. So that means that this content of g of x can't be something greater than 1. The content has to be equal to 1, so I'll just write that down over here. So therefore, actually let's just zoom down a little bit. Therefore, the content of g of x must be 1, which is what we wanted. Moral of the story, g of x is primitive, and therefore every polynomial in zx is factorable into its content times a primitive polynomial. That'll be useful in some of the theorems that we prove later on.